Hello, we're the Senior Design Team 19072. Our design project was titled Benchmarking Signal Processing Complex Math in an ARM General Purpose Processor and was sponsored by General Dynamics. Our team members are Michael Bullock, Kyle Fortuno, Cordell Freeman, Payson Harris, and Michael Inouye. The current hardware that General Dynamics is using for digital signal processing is nearing end of life. As such, General Dynamics needs to find a new alternative to their current systems and would like to ensure they make the best possible choice. Our job in this process is to explore the ARM A64 general purpose processor as a potential replacement. In order to properly test this architecture, our team took 20 common functions from the fixmath.h library that General Dynamics currently uses for digital signal processing and compared how they run on the ARM processor versus the current TI DSP hardware that General Dynamics uses. To do this, we converted each function to a format suitable for the ARM processor using Neon intrinsics where possible, ensured successful compilation of each function, ran them on both the old hardware and prospective new hardware, and compared the performance results of the different hardware. The as-delivered system is converted C code we developed for the ARM system and the performance results we created by benchmarking the 20 specified functions based on clock cycle count. Each function successfully compiles when built using the ARM Cortex-A53 chip in a proper environment. When applicable, these functions were developed to employ the use of ARM architecture intrinsics or Neon technology. Each function runs on a test vector and outputs the same results as the TI DSP board for the same test vector. Single variable statistics of the clock cycle results for each function have been calculated and presented in the 20 performance reports. This system meets the requirements described in our system requirement document. Our planned deliverables for our project include multiple items to document and compare the benchmarks for the given math library on both hardware platforms. The first deliverable is a performance report for each function defined in the fixmath.h library. Each report will include raw clock cycle count statistical analysis, corresponding time statistical analysis, and some single variable statistics for clock cycles for the function on both platforms. In total, there will be 20 performance reports to cover all functions in fixmath.h. In addition to these performance reports, the full source code to produce these results on the ARM Cortex-A53 will be provided. The source code will contain converted functions from fixmath.h, modules to count the clock cycles, and test vectors and functions to be converted from the fixmath.h library. The source code is accompanied by documentation to install and run the source code on a Raspberry Pi 3B Plus so that the results may be reproduced and validated if desired. No source code for producing the TI DSP board clock cycle data is delivered as that was provided by General Dynamics. Lastly, 6 Raspberry Pi 3B Pluses are to be delivered with one already configured and set up to benchmark the ARM Cortex-A53. These deliverables ensure completion of the project and provide comprehensive results. Our design and verification process started with creating a test vector for a function. We then benchmarked the function on the DSP board, recording the output of the function. We then converted the function to work on the ARM processor. We used the same test vector as before to benchmark the ARM processor, also recording the function output. We then compare the function outputs between the DSP board and the ARM processor. If the outputs do not match exactly, the converted ARM function must be corrected and benchmarked again. To benchmark a function, we recorded how many clock cycles were used to complete the function while using the test vector as the function input. We also observed if a function could utilize the Neon intrinsics of the ARM processor. If it could, we developed a second version of the function that utilized the Neon intrinsics and benchmarked it in the same process as the converted ARM function that did not utilize Neon intrinsics. To account for variation in clock cycles needed to complete the benchmark due to factors such as the operating system for the ARM processor, we performed the benchmarks 100 times for each function. We completed this design process for all 20 functions given to us by General Dynamics.
Here, we show a quick demonstration of running a function across both hardware implementations. First, we execute the run_test.py script in Python 3. Since we want to run one function, we will use the -f argument that we have added for ease of use. This builds the C program and runs it on our Raspberry Pi with the ARM Cortex-A53 processor. Now, since the function is done running over the test vector 100 times, we can access the number of clock cycles by opening molt32_arm.txt. Here they are listed, and at the bottom we show single variable statistics. For the TI DSP board, we open our GD provided DSP workspace and run the provided molt32 function. Here, the results are printed to the console. Here, we show a general results table with the difference in mean cycles between the ARM processor and the TI DSP1. Looking at the first entry in the table, for molt32, we see that the difference in mean clock cycles was negative 11%. This means that molt32 required 11% fewer clock cycles on the ARM board to complete the function on average. The two tables below show more in-depth statistics for the molt16 complex VIQ function. In general, the TI DSP board outperformed the ARM processor in terms of raw clock cycles across all functions. However, this does not disqualify the ARM board outright, since it is capable of running functions on 4 cores instead of just the one that's available on the TI DSP board. In addition, its ability to run at a higher clock rate makes it more competitive. Thus, there are trade-offs between the two that must be examined for GD to determine which is best for their applications. The system requirements verification matrix here for molt16 complex VIQ shows the verification methodology used for each system requirement per function. Since our project was 20 discrete tasks that had an overarching structure, it made sense to create SRVMs per function instead of per system. In this function, there were 0 build errors, it had 100% accurate outputs, and it successfully implemented single instruction multiple data or SIMD hardware instructions where applicable. Thus, it passed all of the verification. As our project could essentially be considered a set of 20 distinct tasks, the Agile methodology was well suited for our design in particular. The 20 functions could be broken down sprint by sprint, allowing members of our group to work on several tasks in parallel as the group worked through the entirety of the project. Of course, like any design project, some aspects could have been ironed out smoother. Our DSP board, on loan from our sponsor, General Dynamics, frequently experienced connectivity issues. This could have been avoided, or rather, the risk could have been better mitigated had we purchased a second board with our excess funds. This would have reduced the risk of falling behind on our internal timeline. However, in the end, this did not keep us from completing the project. As a software project, the important deliverables are mostly digital. We will deliver the converted ARM-C source code alongside its accompanying test vectors, test vector generation scripts, and testing framework that allows for rapid execution and performance assessment of the functions. In addition, we will deliver the technical data package with complete performance results for every function to enable General Dynamics to make an informed decision in the future. Finally, we will return all hardware to GD. In conclusion, we were able to complete the project, meeting all of the system requirements agreed on in the proposal. We found the ARM Cortex-A53 to be a competitive substitution for the current DSP hardware solution, with its decent clock cycle performance, faster clock speeds, and better compatibility. At this point, we would like to thank our sponsors, Randy Durr and John Mataram from General Dynamics, for their support in developing this project. We would also like to thank the judges for the consideration of our project. Finally, we thank our mentors, Claude and Kat Merrill, who provided excellent guidance and advice at every step in the development of our design. Thank you for listening.